Hi Math 95. In this video we're going to introduce section 12.1 where we introduce a new kind of function. These are called exponential functions. So let's first consider these functions. These are functions of a completely different form than what we've seen before. Notice that we want to consider the following function. F of x equals 2, and then there's an exponent where there's a variable right here, yes? Or the variable is in the exponent position. The question is, does this look any different than functions we've seen before? And the answer is yes. We haven't seen anything where there's a variable up in the exponent like this before. We've seen things like x squared, but not 2 to the x. So again, the difference is that the x is up here in the exponent, and the base is a specific number. Functions of this form specifically are what are called exponential functions. So in general, we can evaluate these exponential functions if we wanted to plug in a number for x, say. We could use our calculator to evaluate exponential expressions, exponential functions with a number plugged in. The textbook has some instructions for which keys to use, and those instructions appear in section 12.1, and I can also help you in class with any calculator questions you might have. And these tools will be helpful also when we talk about logarithms in the next section also. These exponential functions appear in many real-life situations, including things like population growth, growth of epidemics, radioactive decay, and other changes that involve rapid increase or decrease. For example, interest rate calculations can also be used, you can also use exponential functions as well. So let's work with the definition of an exponential function. An exponential function is a function f with what's called a base b, and it's defined by the following form. We have f of x equals b to the x, or if you don't want to use f of x notation, we could say y equals b to the x, where b is a positive constant. We don't want to let b be a negative number, okay? So b has to be positive. And we also don't want b to be 1, because if b is 1, then we're just doing 1 to a power, which is always 1, and that's not exciting, right? So we want to make sure b is positive and not equal to 1. X can be any real number. This x being any real number gives you a hint about the domain of this function here, because if x is allowed to be any real number, that means you're allowed to plug anything in up here as an exponent, which makes sense because we've worked with negative exponents and positive exponents and fractional exponents. So x really can be any number you like. You can plug it in up there as any number, which means the domain of this function is all real numbers. That's really what that is equivalent to. Okay, so let's just talk about a couple of characteristics really quickly, and these aren't featured in any of our slides, so I'll just make use of making some notes here for you on our special little paper that we have. So first of all, I'd like you to at least get a little bit familiar with what it looks like when you try to evaluate an exponential function. So let's take something like 3 to the x. Okay, and sorry about my slanty writing. I'm using my bamboo tablet at home for the first time and I'm getting used to the new setup. So what if I, for example, wanted to evaluate when x is 2, if I wanted to like plug in 2? Yes, that would mean I would be doing something like this, 3, and then the 2 goes where the exponent is, something like that, yes? So that means that f of 2 is 9 because it is 3 squared, right? So that's how we evaluate an exponential function. The graph of an exponential function, the shape of it depends upon what b is, right? So, so here we should say something like shape depends upon b. Okay, the base. If we get something like this, if b is bigger than 1, then we get a shape that looks like this. So there's our axes, and the shape would look like this. If b is less than 1, and again, remember b has to be a positive number, so that means there's sort of this unspoken bigger than 0 part right there also, then the shape of the exponential graph looks something like this. Oops. Let's make that look a little bit better, because that's just ugly. Let's all agree that that's just ugly. Okay, let's try to make it a little bit nicer. Okay, and we go something like this. Whoop. Okay. For both of these graphs here, as this sort of tail goes out like this, it approaches the x-axis but never actually touches it. The same thing going on here. This one goes out that direction, but it never actually touches this x-axis right there. Okay, the steepness of the graph depends upon how big or small b is, right? So if b is bigger, then this thing is going to be steeper, right? And if b is smaller, it's going to be less steep. It'll be more shallow, right? And the same thing here, right? So if b were larger, for example, let me get a different color. If b were bigger, we would have instead a graph that looked something like this, right? So it gets steeper like that. Okay. What we've already said about these exponential functions is that their domain is all real numbers, right? So the domain is all real numbers. And what else? They each pass through the point 0, 1. And the reason for that is because when you plug in 0 into the function, you're doing b to the 0, which is always 1. Okay? As long as b is not 0, of course, but we know it's not allowed to be 0 because that was our restriction for the exponential function definition. All right, so let's head back to our PowerPoint presentation over here, and let's head to slide number 11. One special base that is made use of for exponential functions is the natural base, or this number e. I know I just said the number e, and that looks like a letter, but it actually is a number. So e is an irrational number, and it's symbolized by the little letter e, and it appears as a base in many applied exponential functions. This irrational number is approximately equal to 2.72, right? And so here we have this approximately, and it's irrational, so the number just keeps going in the decimals, right? E is called the natural base, and the function f of x equals e to the x is the natural exponential function. And there is a button on your calculator for e to the something, right? So try to find that and experiment with it a little bit. Remember, e is not a variable, it's just an irrational number. Okay, some applications of these exponential functions appear in finance and specifically in business applications here. So formulas for compound interest are places where we can make use of exponentials, specifically in what we call continuous compounding. Okay, so these are situations in which you are investing or borrowing a certain amount of money, right? So these are what we call formulas for compound interest. So if, for example, you invest or borrow money for, say, t years, the balance A in an account after those t years, when you borrow an initial value p, right? The principal is p. That's how much you initially borrow or invest. At an annual interest rate, little r, as a decimal. So for example, if r is 5%, you would have to write r as 0.05. And we have the following formulas. If the interest is calculated n times per year, that's what this definition right here means. Compounding n times per year means the interest is calculated n times per year. We can calculate the amount of money in the account A by doing the following. Take the initial amount borrowed or invested, P, multiply it times this scary expression. You just plug in R as a decimal for the interest rate, N is the number of times it's calculated per year, and raise that to a power of N times T. Okay, where N is the number of times it's calculated per year, T is in years that the money sits in the account. Okay, work out that the arithmetic for that, and that'll tell you what the balance of the account is after the T years. If instead the interest is what is called continuously compounded, meaning it's not compounded like twice a year or 3 times a year, it's continuously calculated, then we use the following formula instead. And you'll notice this is exponential. It's p, which is a number, times e to the something, right? Okay. And we can look through some examples in our textbook here for these specific applications of these formulas. But I think this gives us a brief introduction to section 12.1.